Picture the dawn of a new era in physics. It's the early 1960s, and scientists are attempting something almost unimaginable, unifying the forces of nature into a single, coherent framework. This ambitious endeavor would become the standard model of particle physics, a theory that describes the fundamental particles making up our universe and how they interact. In this model, three of nature's four known forces take center stage: electromagnetism, the weak nuclear force, and the strong nuclear force. Out of that glorious chaos of experiments, equations, and brilliant insights came the theoretical prediction of a humble but transformative particle, the Higgs boson. Electroweak theory, as the name suggests, merges electromagnetic interactions with the weak nuclear force, uniting them into a single mathematical framework. Before this unification, scientists treated electricity, magnetism, and the weak force separately, missing a deeper pattern in how particles behave. It was discovered that if you look at high enough energies, the electromagnetic force and the weak force are really just two faces of the same coin. That coin became known as the electroweak interaction, and one of its crowning achievements was explaining how the W and Z bosons, the carriers of the weak force, can be so massive, while the photon, the carrier of electromagnetism, remains massless. The missing link was a mechanism that endowed certain particles with mass while leaving others unscathed. Meanwhile, quantum chromodynamics describes a different realm altogether: the strong nuclear force, which binds quarks together inside protons and neutrons. The chromo in quantum chromodynamics refers to a property called color charge, nothing to do with visible colors, but an abstract label that determines how quarks and gluons interact. This theory explains why protons and neutrons remain so tightly bound that it takes immense energy to break them apart. Together, electroweak theory and quantum chromodynamics form the backbone of the standard model, but there was still a nagging problem. How do particles like the W and Z bosons, quarks, and electrons actually acquire their masses without breaking these beautiful symmetries? In 1964, a handful of theorists, including Peter Higgs, Francois Englert, and Robert Brout, proposed an elegant solution. They posited that the entire universe is permeated by a field, later dubbed the Higgs Field. As certain particles travel through this field, they slow down in a sense, gaining mass in the process. Others, like the photon, glide through it unaffected and remain massless. This was a brilliant theoretical leap, but proof of its reality required detecting a new particle, the Higgs boson, a tiny ripple in the otherwise uniform Higgs field. Decades passed without success, as scientists built particle accelerators capable of ever higher energies, each time hoping to produce evidence of the Higgs. It wasn't until the early 21st century that the Large Hadron Collider, an enormous machine buried underground near Geneva, had the raw power to smash protons together at energies high enough to reveal this long-sought particle. In July of 2012, two experiments at the LHC called ATLAS and CMS announced the discovery of a new particle consistent with the Higgs boson. It was more than just an exotic find. It validated half a century of theoretical work and confirmed that the mechanism giving mass to fundamental particles was correct. In recognition of this monumental breakthrough, Peter Higgs and Francois Englert were awarded the Nobel Prize in Physics in 2013. Although Robert Brout had passed away and thus was not eligible for the prize, his contributions remain enshrined in physics history. Their theory not only completed the standard model by explaining the origin of mass for the W and Z bosons, quarks, and electrons, but also reinforced the unification at the heart of electroweak theory. Without the Higgs mechanism, our current picture of the subatomic world wouldn't just be incomplete, it might be unrecognizable. Of course, the standard model is not the final word on the universe. It leaves out gravity and doesn't explain puzzles like dark matter or why neutrinos possess tiny masses. Quantum chromodynamics, for all its success in describing how quarks bind to form protons and neutrons, still can't unlock the mystery of why the strong force behaves so differently at large distances compared to small ones. Yet the discovery of the Higgs boson was a game-changer, giving us a crucial piece of the cosmic puzzle and opening new doors for exploring realms of physics that might lie beyond our current theories. In laboratories worldwide, physicists continue to refine measurements of the Higgs boson's properties, searching for the smallest deviations that might signal new physics. Every collision at the Large Hadron Collider still carries the promise of revealing fresh surprises, maybe exotic particles that point to the existence of dark matter, or subtle effects hinting at entirely new interactions. The Higgs boson's discovery was, in many ways, the end of one chapter and the start of another. The journey continues, powered by the same curiosity and ingenuity that drove Higgs, Englert, and their contemporaries to ask one simple yet transformative question: how exactly do particles get their mass?